Hello everyone, this is Mohsen Saraj from Ozen Engineering. Today I want to talk about uh, an example for scripting that uh, have to create that by recording what we are going to do in uh, ANSYS Electronic Desktop Icepak AEDT. And basically this script is for simply about the cut planes, so which a little bit work on that after creating that to customize that to create additional cut planes for post processing. This is the model that you are seeing that as you can see in the model we have fans, okay, fan 1 and fan 2, generic components like we have heatsink, also we have PVC imported here. We have some solids that like a bridge, as you can see, DDR memories, and also large flash memory and small flash memories. So this is what we have here. Also uh, in the thermal, these are the boundary conditions that we have. We have some boundary condition for the power, 2.5 watt, for example, for this one bridge, another 2.5 TDRs, each 1.1 to 1.125 watts, large flash memory, a small flash memory, as you can see here in the property table. Also we have some boundary condition for the grid here that you can see. If you want to see the properties, you can see that. And for the side walls, that you can see it here, okay. For the side walls we have thermal boundary conditions for heat dissipation, that it is in terms of the heat transfer coefficient. And uh, we can also check the power budget to see that how much is the total power applied here by the components. So this is about the model that we have. If you look at here, we can check also the materials. For example, these are all the components have ceramics for the material. For example, I can check it. What is the material? It is ceramic material. And we have the thermal properties here for it. For another material, all of these have ceramic material. This one is high conductivity material for AGF. Okay, again, if I want to check the materials, you can see that. And these are the material properties, mostly thermal properties that we have. So we have a library of the materials, or we can export or import the material information and read it here. Also I imported IDF file here. These are the components that you can see that. If I want to see the what we have here for PVC board, okay, these are the copper traces that you can see here that we have. I can back to ECAD model that we have it here and CAD model. So this is about the model. Here I just want to show you that how to quickly set up the model, run it, and then for post processing I'm going to create a cut plane and recorded it for scripting, and then use that script, customize that, and then use it, reuse it for automated, there's customization and automation of the kind of post-processing operation that I want. Yeah, I can also, before solving for convergence, I can check and set up some monitors here. I can come here and say that assign monitors, it could be assigned to a face or to a point. So I need to first choose the face or point and then come here and assign it. For example, for the board, okay, I have this, it is for the temperature, monitor the temperature of the bridge, and also temperature of the DDRs, and for large flash memory. These are all for the temperature. I can, for example, for this phase, come and assign also flow monitors. Okay, for example, so mass flow rate or volume flow rate going out or in this phase. So I can now come and run it. Okay, before that, let's check the setup for the solution. 500 iterations, the maximum that I considered for running the simulation. I want to solve temperature and flow fluid, not only thermal conditions. Also, I'm considering fluent turbulent models. No heat radiation here. And for convergence, for the residuals, I consider this value for flow residual, and for sure higher value, much smaller value for uh, residuals for energy. Solver setup, basically these are like initial boundary conditions that we have it here, and I can also, if I want to change the under relaxation factor, I can do it here, and also for the discretization, if I want to change the scheme for the discretization, first order, second order, or for the pressure standard or other presto. These are similar coupling method that we had from Fluent. So these are the setup that we have. Also, to check the ambient condition, you can come to the desktop and design setting, 20 degree for the temperature, degree Celsius, 0 gauge pressure, and this is same 20 degree for radiation temperature. These are the ambient condition. Gravity, if I want to consider that in the z direction, okay, negative, and the other things if I want to work on that. So let's come here and start the simulation. I can right click here and go for the residuals. You can see that the steps that are taking for the solving the model. The thermofluid solution has not been started yet. So we are starting to see the residuals and the iterations for the solution. And for monitors, we can check the monitors here. We already have 3 monitors for the temperature of DDR, flash memories, and the bridge. We don't have any fellow monitor. So let's back to the iterations. So I stop the video here and I will back when the solution is completed. The solution is done. You can see the residuals. Let's check the monitors. This is monitors for DDRs. The max temperature is up to about 63, 64. This one it is the monitor of temperature of the bridge, and the maximum temperature of that is a little bit below 50 degree Celsius. And the last one, this is the temperature, monitoring temperature for large flash memory, and maximum it is like 36, 37 degree. So we're good here. Let's start uh, go for the scripting. Before scripting, let's check the mesh a little bit. We can go for the mesh viewer here, okay, in the simulation tab, okay, in this section mesh viewer. We have about less than 500,000 cells, okay, 470,000 cells almost, okay. Even if I want to show the cut plane, this is in X direction. That if I want to check the mesh, you can see that, okay, the way that we mesh it, these are all by default setting that we have it. And I can go for different this is, I guess, X cut plane. I can move it around to see that, oh, what's going on. Or here at the DDRs, you can see the mesh. Also, if I change the cut plane, for example, say that in Z direction, okay, you can see the mesh. Also check the mesh here, if you want to do some changes or not. We just use the default setup for the mesh. If we want to check a specific body mesh, okay, say that for example this one, we can see the mesh for the DDRs. You can see it here, one of the DDRs. Or if I check these fins on the heatsink, you can see the mesh also here. So this is for the body. If I want to go for a specific geometry, part of component of the geometry or that, okay. And this is for the walls that you can see. Back to cut plane that I already showed you. Let's check the quality. The quality for face alignment, you can see the minimum it is 0.4. Good. If I check the volume and then skewness, I can check it. For example, the minimum it is like something's for this part. If I click here, you can see where I have that low skewness for the mesh around the the fans that we have. Or for the face alignment, come here, for example, in this range, you can see that again where I have element with this range for the face alignment. So you can see the elements in the mesh. You can check the quality of the mesh by face alignment, volume, or skewness. And for the mesh display, you can see that here. Let's go for scripting. save the solution, and then in the automation we can start recording the script. So from now on, when whatever I will do that, it will be create a plot based on that. I can say the record script to the file and give it a name, like I say that uh, plot cut plane, for example. Save it, and now we start working on the post processing. Let's first create a plane. Come to the draw, the main menu, and then create a draw plane for the uh, for this, for example, this fan. Click in the center and then in this direction. So we now creating a plane. You can see it here. This is the plane that I created. Click on the plane. You can come here to the field overlays and say that plot fields, temperature, and then I can give it a name or use the same name that I have, and done. Yeah, this is the contour for the temperature on this plane. As you can see, maximum it is 26.76 degree, and this is here. So basically I created like a draw plane or cut plane and plot the contours of the temperature on this one. Then I can export this cut plane and save it. I can say that export, it could be JPEG. I can say that, for example, cut plane temperature, and save it. So back to the automation and say that stop recording. Let's look at the script. I use Visual Basics editor. If you have another editor, you can use it to see the Python script. As you can see at the beginning, okay, it is populated with initializing the project, selecting the current project, okay, and the Icepak design that we have it, okay. And after that we have one block, one editor for create cut plane that we have, and these are the various parameters to design the cut plane that we have. The first cut plane that I have it here, and this is the name that I use it for it. So next module is the one that I create the temperature one plot here. You see that the information populated here for the temperature plot, and I use plane one cut plane here, okay, that I have it. I already designed the cut plane here. And the last block or last module, it is for saving the uh, the plot on the cut plane as a JPEG file that I have in the desired location that I want it. that this is the address bar for it. Okay, JPEG format and the resolution for that. So these are the main modules for that created by Icepak itself, just by recording the workflow that I had done in Icepak when preparing the cut plane, and use that cut plane to create a plot for the temperature across that, and saving it as an image file with the JPEG format. Now I want to just do some changes to that for kind of automating post processing. This is the new uh, code. So I added this part. It is basically a loop for creating multiple cut planes, multiple cuts. uh, I consider a range from minus 25 millimeter up to position of 175 millimeter in each direction, with the increment of 50 millimeter. I use num parameter variable for looping, and then define the cut planes with the word plane with the extension in with this one, which shows that what is the plane, the cut plane, number one, number two, whatever, and then have the temperature into the name, and with the string, that string it is for the adding the again the number, and for post name for the image file, and also plane exposition, it is shows that what at what position this cut plane is 20 minus 25, 25, 75, 125 and 175 millimeter. So one thing that you need to be careful about, that to not get syntax error, is the indentation. You see that indentation, it is based on this for in the original code. This is the indentation that we have in the modified one. Be careful about this indentation, that all these modules for cut plane, for create the field plot, and also for exporting and saving, these ones should be inside this loop. uh, for the I use the plane exposition, this line, okay, as a name for that, to set the exposition here. Previously I had it with a constant number 19 minus 19 millimeter. Now I have it with the position of the cut plane. This is one change that I need to you need to do it here. Another one is for the name, okay, in this line, that I use plane 1 name here, this plane 1 name here. Originally, now in the new code I use plane name, that plane name defined here on top. Okay, you can see that. These are the changes in the first module for create cut planes. Then in the next module for creating the feed plot for temperature, you know that here I use temperature 1 name here in the original uh, script, which is here, given here when I created the plot on the for the temperature 1. You can see that here, name temperature 1. Now I'm using post name, okay, and you see the post name is given here. Okay, so it could be temperature 1, temperature 2, temperature 3. You will see that we will have more on this list here when we run this new code. This is one change in the second module. Another change here is that I'm using the name for the plane code. Originally it is plane 1 that I created. Now I'm going to use again plane name here, that it is plane 1, plane 2, plane 3, plane 4, with use of this string here. Rest are the same in this module, and in the last module, for saving as a JPEG image the contour that I created, I use this I use the same address, the same location, the working directory that I have, so I use it here as you can see, and I add these 3 lines here in the last module. Okay, before the last module, this is the last module, so before the last module I added these 3 lines. First one, it is path route. I define path route here, and then I use this path route. Okay, now before that, for the file name, to give it a name, for the images JPEG files, I use the name temp cut x plus a string that it is you remember that plane x position is here. Okay, that is gives me the position in x direction in millimeter. So this is for the file name and JPEG format, and then in the file path I use the file the path route, okay, plus file name, and then in the arguments here in the original file I have the argument here that it is the address bar, it is where the working directory is. You remember that JPEG format and the resolution. Okay, in my code that I just created by help of the ANSYS resources that we have, I have this file path, new file path with the new resolution, and the rest is the same as before. So these are the changes that I made to the original code. I created under different name in the same working directory, and then I'm going to use this new code for automating creating multiple cut planes, and then create plot temperature plot on each of these cut planes, and save these images as an image file as a JPEG file. Let's go and run this new code. So this is the model in the automation part. Go for run script. I created this script and see. So you can see that the new code planes created one by one, and we're going to have the contours on that. One, 2, 3, 4, 5, 6 that we have, and these are the files we have. Okay, you can see that 125, 25 minus 25, 75. So we first of all, with this new script we could create multiple cut planes. This is the first thing, and second, we could save these contours in these cut planes in the JPEG files here. So in this video I wanted to show you that how to create a script in Icepak AEDT here in the automation section, if you come to the Deduce tab and click here to record script, so whatever you done after that, it will be translated into the Python script. I first here created a draw plane and use it as a cut plane, this plane here, and plot the temperature across that plane, and then save it. Okay, you remember that. Okay, I just came to the modeler and export that, save it in the JPEG file format. So this script, okay, showed you that have to do this. Okay, here this is the original one that I created, and then I work on this original code and converted that to the code that I can have basically multiple plane code created, and then on each of that we can have the plot for the plot for the plot for the temperature, and then save it in the working directory or working folder that we have it here. We have the model there. So hopefully you can learn a little bit about how to start scripting in Icepak ANSYS AEDT. Thank you very much for watching this video.